Hello everyone. Sorry I couldn't be here today, but as far as starting off today, yesterday you looked at the first section of 8.4, which is on investigation of the properties of circles, things like diameter, radius, and circumference and area of circles. So we looked at that yesterday. With that being said, there were some homework questions that you were assigned for the first section of 8.4, so if you would please have those out. I'm going to put the answers up for those right here. So if you'd like, you could pause the video right now and take a chance to correct your homework from last night. So pause the video now, go through the questions that were assigned and correct yours. When I get back, then I will go over these for credit. But for right now, just correct yours to see which ones you have questions about so we can address them when I get back. So pause the video now. Okay, welcome back. With that then, you can put those away and then have your note packets out to the second day of 8.4. It'll look like this. It says 8.4-2. It's on rings. To start, we're going to do a warm-up question. The warm-up question is investigating one of the properties that we looked at yesterday for circles, which is the circumference. The circumference is the distance around the outside of a circle. You can think of it as the perimeter of the circle. So if you have a circle, the distance around the outside of the circle is its perimeter, and the perimeter for a circle we call circumference. Circumference is equal to 2 pi times its radius. This one I want to know is, here's a baseball field. It's 320 feet from home plate to the right and left poles down the outfield line. My question is, how much fencing would be required to make the outfield? And I've kind of sketched it right here in this blue line. You can think about it in terms of a circle. Because this is a 90-degree angle, it will end up looking like being a quarter of a circle's circumference. So can you use the idea that you know the total circumference of a circle? Here we're trying to find a quarter of that, and then you know what looks to be the radius of the circle right here. So warm-up question, take 2 minutes, try to use what you learned yesterday to find how much fencing would be required for the outside outfield of a baseball field. Pause the video now and then come back after everyone's had maybe about a minute, 2 minutes to try it. Okay, welcome back. Let's go over it. Like I said, the circumference of an entire circle is 2 pi r. Here we're trying to find a quarter of it. So the outfield fence, the fence is going to be 2 pi r divided by 4 because it's a quarter of an entire circle. So I substitute in 320. So 2 pi times 320 divided by 4. And I grab my calculator. 2 pi times 320 divided by 4 tells me about 503 feet of fencing, if I round to the nearest foot, would be required. It looked like 502.7. So round to the nearest foot, get about 503 feet of fencing. That was yesterday. Today what we're going to look at are rings. Rings are just like circles with inside circles, like a washer. So in order to determine what the weight of a washer would be, maybe if a company is going to order a ton and they're worried about shipping costs, first they need to find how much area it takes, and then it might be useful to know maybe its density in order to find the weight of it. But you first need to be able to find the area of this ring, something like so. We'll come back to this question. I want to know what its area is, and this is used a lot. Machining, boring, drilling, and tapping are all important processes that are involved in removing material and you're creating some hole. So what I'm going to show right now is a little YouTube clip. It's a crash course in milling. It's going to be about 4 minutes long. So I'm going to expand the screen now and just play it. You might need to turn the speakers up because I'm playing a YouTube video through a recorded screencast. So hopefully it turns out okay. So we're going to try it right now. So this is just to see where rings, or drilling, or milling is what it's called in machining, is applied to the mathematical skills that we're going to be talking about today.
Drills are the most commonly used tools for creating holes. Short spotting drills are used to create shallow, conical holes, preventing longer drills from wandering off center. Frequent retracting, known as peck drilling, helps clear chips. Screw machine drills are much shorter and can drill straight, accurate holes without spotting. Programming a CNC machine to drill holes is simplified with the use of canned cycles. The table and spindle initially traverse to the starting position of the first hole. The G81 command, followed by various parameters, initiates the can cycle. G81 is a modal command, meaning it stays active until another command cancels it. Drilling additional holes only requires specifying new coordinates. Drilling into an angled surface requires spot facing using the center cutting end mill. After spot facing, a standard drill can be used. Chucking reamers are used to enlarge pre-drilled holes to very precise diameters. Slow speeds as well as coolant or lubricant should be used. Power tapping is a fast way to tap holes on a conventional machine equipped with a quill and a 3-phase instant reversing motor. Synchronized rigid tapping on a CNC machine is accomplished using the G84 can cycle. Helical boring with an end mill is an economical way of creating larger holes. Deeper holes can be made using a boring head. The adjustable twin cutter unit shown here is used to enlarge pre-drilled holes. A finish boring head holds a single adjustable cutting edge for the highest precision and the smoothest finish.
So the reason I chose to show that was because some of you spend hour to hours on those machines every day, and some of you don't even know that out in the machine shops they're using CNC machines daily. So it's pretty cool, and the things that they were doing are actually going to be quite connected to the topics that we discuss today, because we're talking about circles and rings, and that's used heavily in CNC machining. So like I said, we use it when we're trying to find areas of washers. We'll come back to that question. The first thing that we're going to do is when talking about a ring, well, it's actually not that difficult of a concept, because if you understand how to find the area of a single circle, a ring is nothing more than punching out the middle. So for example, if I wanted to find the area of a ring, all I need to do is find the area of the outer circle and subtract the area of the inner circle. I'm just punching out the middle part. And so they give the formula that the area is equal to pi r squared, because that's the area for any circle. The area for any circle is pi times its radius squared. If it's the big circle, we'll use a big radius, minus the inside circle. They say, hey, they're both being multiplied by pi here, so you can factor that out, but that's probably more math than you need. Really all you need to know is the area is equal to the large area minus the small area. And that's all we're going to do. This is actually used a lot. For example, if I was going to create a sidewalk around maybe a tree area in a park, I'm actually doing a ring. So for example, this says how many square yards of concrete surface are there in a walkway that's 8 feet wide surrounding a tree if the inside diameter is 16 feet. So imagine this. Here, let's do like an overhead view. Like if I was a bird flying in the sky and I look down and here's this tree. from the tree center to the inner edge of the walkway is 16 feet, and then the walkway itself is 8 feet in width. So what I want to do is I'm trying to find, the area of this walkway here that I'm shading in kind of this red. Well, in order to find that, I need to find the area of the outside minus the area of the inside. So the area of the outside is from center of the tree to the very edge of the sidewalk. Well, that radius is 16 plus the width of the sidewalk is 8. So the radius of the big circle is going to be 16 plus 8 would be 24. So the area of this big circle right here is going to be pi times 24 squared. The area of the inside part, which I've shaded in green, could be the grass, is going to be using a radius of 16 because it's 16 feet from the center of the tree to the inner edge of the sidewalk. So the area of the green part, the green grass, is going to be pi times 16 squared. So the area of the outer is pi times 24 squared, and pi times 24 squared is about 1809. The area of the inside is pi times 16 squared. That's 804, rounding to the nearest foot here. And then I subtract them, because it's outer minus inner. When I subtract those two, what I'm going to get is 1,005 square feet. That's how many square feet I would need of concrete. Okay. Good to go. So there's the first example of a ring is if I was going to decide or calculate how much concrete I would need. Example right there. Leading question would be area of the washer. So in order to determine what the weight of the wash will be once it's made, one must first find its cross-sectional area. So the area, looking just straight down at it. So the area is going to be the bigger circle here. I could highlight in maybe this yellow. So the area of this big circle is the outside edge. And outside edge is from center to outside edge is 7/16 of an inch. So its area is going to be pi times 7/16 squared. The area of the inside one is going to be this inside circle. I'm going to subtract out. I'm going to highlight here in green. In order to find its radius, I need to think a little bit. And the way I'm going to do it is, okay, it's 7/16 from center to edge. This is an eighth, so here to here must be 7/16 minus 1/8. How do we subtract fractions? We make a common denominator. 7/16 minus 2/16 is equal to 5/16. So here to here is 5/16. So the area of the inner part that I'm going to punch out would be pi times 5/16 squared. And then I subtract those two. So pi times 7/16 squared minus pi times 5/16 squared. Grab my calculator, go through it. I end up getting 0.29, and my units are inches by inches, so inches squared. That would be the cross-sectional area. Then you'd have to look up maybe some things like its density of the material in order to begin to calculate what its weight would be once you have its area. You would need its density. You'd also need to know how thick it is. So you'd actually eventually, and that's what we move on into in the next chapter, is getting volumes. So I'd have to take this cross-sectional area and multiply by the thickness of the washer. That would give me its volume. Then once I had volume and the density of the material, I could start to calculate the weight. And that would be important for things like shipping, or if I was going to put it on things like the washers are used heavily in rockets. In rockets, you want things to be light as possible, so that would be a really good application. Your turn to try a ring question. What is the cross-sectional area of a steel collar 0.6 centimeters thick with an inside diameter of 9.4 centimeters? So what they're saying is, if I draw a picture here, steel collars used around pipes a lot of the times. So it looks like this. They told us the inside diameter is 9.4. And the thickness of the collar right there is 0.6 centimeters. This was centimeters as well. So your job is to try to find out what the area would be of the collar. I'll do it here in blue. So what's the area of this blue section? Okay. Since it's your turn, you pause the video now. Give it 2 minutes for everyone to try. Once you have an answer, compare with your neighbor, talk through it, and then see if you guys agree before pressing play again. So pause the video now so that everyone can try, come back after everyone's had a chance. Okay, welcome back. First thing we need to do is find the radius, because we're calculating areas, and areas you need radius from the center to the far outside edge. Well, if this is 9.4, that means from here to here is half of 9.4, and half of 9.4 is 4.7. So that means from center all the way to the outer edge is 4.7 plus 0.6. So your big radius is going to be 4.7 plus 0.6 will be 5.3. So I'm going to use 5.3 as my r in the big one. So my pi r squared, my large circle, is going to be found by doing pi times 5.3 squared minus the inside circle has a radius I just found of 4.7, so it'll be pi minus 4.7 squared. Now I just run my calculator. So grab your calculator and run through it. When you do so, you should end up with a cross-sectional area for the collar that's equal to 18.85. Your units are centimeters squared. That's how you find areas of rings. Okay, and like I said, super helpful. I put it in the notes, I'm saying it now. Draw a picture first. Draw a picture and know that you need to use the radius. So drawing a picture and then will help you find the radius in order to do calculations with areas of circles. Okay, so quick review of 6.4. How it's going to work is going to be we need to know things like the area and circumference of the circles. So the area of the circle, I need to know its radius. So from here to here is its radius, and the area of a circle is equal to pi times its radius squared. Let's zoom in a little bit. Its circumference, again, like I said earlier, is perimeter, it's distance around. And the formula for the circumference of a circle is 2 times pi times its radius. Those two things will allow us to calculate a variety of items for circles. So for example, yesterday we did a question about the area for a semicircular window that's going to be made of stained glass. Now I'm going to follow that up and say, how much will it cost? Because that's really what a company would do. So the first thing we need to do is review, how did we find the semicircular area? So if I draw a picture of this thing, you have some stained glass, has a radius from here to there of 9 inches. So I know its area is going to be pi times 9 squared, or 81 pi, because that's what 9 squared is 81. So 81 pi tells me its cross-sectional area is going to be 254.5 square feet. Oh, sorry. That's going to be, well, we got to be careful here because I was going too fast. I see this is 9 inches, so that's actually going to be, let's go back. That's going to be square inches. The problem here is our total cost goes at $250 per square foot. So I need to get 254 inches squared to be square feet. So this is a good exercise in what we did in chapter 5. I have 254.5 inches squared, and I need to know how many square feet is that. Well, I remind myself how many inches are there in 1 foot. Well, 12 inches per 1 foot, but only one of those gets me out of one of the dimensions. So now I'm still in inches. I need to do one more in order to get me out of inches and into feet. Because it was inches squared, I need to do this twice. So I do it one last time, and I take 254 divided by 12 times 12. So really it's 254, or 254.5 divided by 144. That gives me 1.77 square feet. much more reasonable. 1.77 square feet. And I know it's $250 per square foot, so my total cost is going to be $250 per square foot. I have 1.77 square feet, so 1.77 times 250. Total cost of that stained glass is going to be $442. Whoa, I don't know how that happened. And 50 cents. So it's a good review question. It kind of ties in a lot of things. It ties in area, it ties in unit conversion from Chapter 5, and then it ties in how do you calculate a cost when you know a rate, $250 per square foot. Last example, and then I'll let you try one more, and then I'll be it for rings and actually the study of circles. A hose must fit over a cylindrical opening, 57.2 millimeters in diameter. If the hose wall is 3 millimeters thick, what length of clamp strap is needed to go around the hose connection? So here is my strap. I'm trying to look at how wide it should be set, based on the hose that I have. So the hose right now, they're telling me, has an opening of 57.2 millimeters in diameter. So I'm going to draw a picture here. If I look down the hose, in diameter it's 57.2. So its radius, and that's important, I'm just going to do it right now, cut that 57.2 in half because its diameter is 57.2. Its radius must be half of that. It must be 28.6 millimeters. Now I'm going to use the thickness of the hose, and I'm really exaggerating this because it's a lot thinner than this, but I need to be able to write in here. The hose itself is an extra 3 millimeters thick, and they want to know what length of strap is going to be needed to go around the hose connection. So that's a circumference. So they're asking how all the way long of a strap am I going to need, if I look like right here, in order to go all the way around. So I first need to know what the total radius is. The total radius, big R, is 28.6 plus 3. That's 31.6 millimeters. The length of the strap, clamp strap that would be needed, is the circumference. And circumference is equal to 2 pi times my radius. My radius is the big radius, because that's all the way, it's got to go all the way around the outside. So this will be 2 pi times 31.6. 2 times pi times 31.6 tells me that strap needs to be 198.5 millimeters long in order for me to be able to fit it around that hose. Okay, that's used a ton in the automotives. Last question is for you. It says, in making a turn on a road, the outside wheels of a car must travel 8.7 feet farther than the inside wheels. And that's kind of something that you probably take for granted. And so what I want to show you before I just throw you into this question is what's called the differential on a car. And the differential is what makes it so that the outside tires in a turn can account for the fact that they're traveling a farther distance. So check this out. So there's a variety of properties or reasons, jobs of the differential, which is a car part. One of them is the fact that as a car makes a turn, so for example, as this car made this turn, look what happens here. Here's two paths that the wheels travel. You can see this inside path is shorter, and the outside path is longer because it's farther away. It has a larger radius. So these outside wheels here are going to have to turn more quickly, or they make more turns because they're traveling a farther distance. So this inside wheel and these outside wheels are not making the same turns. And the part in the car that enables this to occur is called the differential. Yeah. So the key idea here is the outside wheels in a turn are going to have to travel faster. They're going to have to make more turns. So how does a car do that with the axle all being tied to the same thing? Well, you use the differential. So the differential allows a car to do something like this. So let's say the outside wheels in that turn we just saw, let's say the path difference between this outside path and the inside path happened to be 8.7 feet farther than the inside wheels had to travel. If the tires themselves are 23 inches in diameter, how many extra turns do the outside wheels have to make during that turn? And the hint is, in one turn, a tire travels a distance equal to its circumference. So the way to think about that is, if I have a tire, and it starts right here on the ground, as that tire rolls forward, it's going to roll in one turn. It's going to travel all the way around until it touches back down here again, and that distance all the way around is going to be its circumference. So once it's made one turn all the way over here, this distance from here to here has to be the circumference of the tire. So that distance right here is 2 pi times the tire's radius. With that and a little critical thinking, can you use the information supplied here, the fact that the outside tires traveled 8.7 feet farther and the tires themselves are 23 inches in diameter, to tell me how many additional turns the outside wheels have to make for this turn? So pause the video now, give it as good of a shot as you can. This one's a little bit more challenging than others. It'll make some of you really think, and some of you might enjoy the challenge. Give this one a try. Take maybe 2 minutes, draw some pictures if it helps you. After 2 minutes, come back and we'll go over it. Okay, welcome back. Let's go over it. So the first thing it says is that the car travels 8.7 feet farther. Well, the first thing we should figure out is how far does the car actually move each time the tires just spin once forward. So it told us that the tires are 23 inches in diameter. That means in order to find how far they travel, I need to find what the circumference of the tires are. And the circumference is 2 pi times the radius. 2 pi, well, the radius of the tires is half of 23, and half of 23 is 11.5. So the circumference of the tires is going to be 2 times pi times 11.5, which is equal to 72.26 inches. Well, the problem is that's in inches, that's in feet, so let's get 72.26 inches into feet. So take that answer of 72.26 and divide it by 12. So we see that in one turn, the car moves forward 6.02 feet per one turn. Okay, now the question is, how many extra turns do those outside wheels have to make? Well, they're going to travel 8.7 feet further, so that's at least one extra turn that the outside wheels have to make. And how many extra turns is it? Well, I divide it. I take 8.75 and divide it by 6.02. So 8.75 feet. I'm trying to get from feet to turns, so I'm going to use my unit conversion. I know there's 6.02 feet in every one turn for the tires. So this is again a chapter 5 review of conversion, cancels feet with feet. My units are now turns. 8.75 divided by 6.02 tells me that in every single movement forward in that particular move around that corner, the outside wheels needed to travel 1.45 extra turns compared to the inside wheels. And what allows a car to do that is called the differential. That's pretty amazing. That is the end of our study with circles and rings. We, for the homework, are on the second day for 8.4. Answers will be right here. What I'm actually going to do right now is pull up the assignment sheet. So here we are at chapter 8. Chapter 8, the second day. So the questions are B1, C5, 6, 15, 17, 19, and 25. And actually with that, because there's only one section after this last quiz that we took, in order to do 8.4, I've actually made a take-home quiz, so that our guest teacher will pass that out for you. So your homework to complete is to do those homework questions of B and C, and then there's a few questions that are acting as a quiz. It's a take-home quiz, so that means this is to be done on your own. You're not allowed to consult somebody else, so if I see that you and somebody else have almost duplicate work, you will both receive 0 for this. This is supposed to be on your own. And then as you're taking it on your own, I do request that once you've tried the homework, treat it just like a normal quiz, where you should be only using your homework and your calculator as you complete the take-home quiz part. It's just a few questions, just so I can kind of give you feedback on how you did with the circle section before our test. So your homework is going to be these questions from B and C, and then the take-home quiz that our guest teacher will pass out to you as well. So that is the end of today. As you're working through the homework questions to help prepare you for the quiz, the answers are right here, so you could pause the video and leave it here, and then I will be back soon in order to kind of provide help and then also give you some feedback on those quizzes. So that is it. I hope you have a good rest of your day. Thank you.